40 light-years from Earth, orbiting a star much smaller and cooler than the Sun, is a planetary system unlike anything in our solar neighborhood. 7 planets, each nearly the size of Earth, closely surround their dim host. Their orbits are so compact that all 7 could fit within the path of Mercury around the Sun. Yet despite their proximity to the star, some of these worlds might have ideal conditions to support life as we know it, or perhaps life as we never imagined. Among them is a world that stands out, a planet locked in just the right zone where liquid water could exist, a planet that might possess a stable enough atmosphere to survive the turbulent youth of its star. This system, named TRAPPIST-1, is more than just a collection of rocky worlds. It may hold answers to one of humanity's most enduring questions: are we alone in the universe? The TRAPPIST-1 system is one of the most intriguing and sensational star systems discovered in the last few decades. Orbiting a red dwarf star approximately 40 light-years from us, there are 7 Earth-sized planets. Unlike the Sun, a G-type main sequence star, TRAPPIST-1 is an ultra-cool dwarf. It's significantly smaller than the Sun, with a radius of just 12% of the Sun and a much cooler surface temperature of about 4,040 degrees Fahrenheit. These characteristics result in much lower luminosity. The 7 planets in the TRAPPIST system are on remarkably close orbits. Even the farthest one, TRAPPIST-1H, orbits its star at a distance closer than Mercury's orbit around the Sun. Yet due to the red dwarf's low energy output, these planets do not experience the scorching temperatures like Mercury. 3 of these planets, TRAPPIST-1E, TRAPPIST-1F, and TRAPPIST-1G, are located in the so-called Goldilocks zone, where conditions might allow liquid water to exist on their surfaces. One of the most fascinating aspects of the TRAPPIST-1 system is its age, estimated at about 7.6 billion years, significantly older than our solar system. This extended time frame could have given more time for potential life to emerge, assuming the conditions were suitable. However, this longevity also raises questions about the star's activity over billions of years. We'll circle back to that. The compactness of this system creates unique dynamics. The gravitational interactions between the planets are strong, leading to resonance patterns that provide insight into their masses and densities. These resonances, observed through transit timing variations, confirm that the planets are likely rocky rather than gas planets. While the proximity of these planets to their host star raises questions about their habitability, it also causes problems. However, current studies suggest that at least one planet, TRAPPIST-1E, might have retained a secondary atmosphere, making it a prime candidate for further exploration. The research of atmospheres around the TRAPPIST-1 planets have been driven by revolutionary observations using space telescopes, each of them contributing to studying this star system. The Hubble Space Telescope, equipped to work in a near-infrared range, played a foundational role in observing this system. Using the method of transmission spectroscopy, HST analyzed starlight as it passed through the exoplanet's atmospheres during transits. This method revealed the absence of thick hydrogen-dominated atmospheres on planets like TRAPPIST-1b and TRAPPIST-1c. Hubble's findings, though limited by its aperture and wavelength sensitivity, paved the way for more detailed investigations. Observations using this telescope ruled out Neptune-like atmospheres with substantial hydrogen and helium, narrowing the possibilities to either dense atmospheres or bare, rocky surfaces. The James Webb Space Telescope has taken the exploration of TRAPPIST-1 to a new level. Unlike Hubble, JWST is optimized for infrared observations, crucial for detecting key atmospheric markers like water vapor, carbon dioxide, and oxygen. Its superior light-gathering capabilities enable it to distinguish subtle features in thermal and transmission spectra of these planets, even under the faint light of the host star. One of JWST's most significant achievements has been detecting thermal emissions from the inner TRAPPIST-1 planets. For instance, secondary eclipse observations of TRAPPIST-1b revealed a lack of significant heat redistribution, consistent with a bare rock planet devoid of an atmosphere. These measurements were made by isolating the planet's thermal signature as it passed behind the host star. While results for the planets closer to the star generally strongly suggest they lack atmospheres, the focus has now shifted to the planets within the habitable zone. However, it's not all that simple. Let us first bring attention to red dwarfs to understand the bigger picture. Why do these stars present significant challenges for hosting habitable planets, particularly in the early stages of their development? Unlike the relatively stable evolution of stars like the Sun, red dwarfs experience prolonged periods of high-energy radiation in their pre-main sequence phase. This phase can last for several 100 million years, during which the star emits extreme levels of ultraviolet and X-ray radiation. The intensity of this radiation is determined by the internal dynamics of the star. Being smaller and cooler than stars like the Sun, red dwarfs exhibit a higher degree of convection. Turbulent plasma movement generates powerful magnetic fields that frequently realign, causing flares. These stellar flares, often more intense than those observed on the Sun, release bursts of energy capable of destroying a planet's atmosphere. High-energy photons coming from the star ionize the upper layers of a planet's atmosphere, heating it to the point where atoms and molecules reach escape velocity. This process, known as hydrodynamic escape, is particularly effective at removing lighter elements like hydrogen, which are the primary components of primordial atmospheres formed during planetary accretion. Over time, this continuous bombardment can also strip heavier molecules like carbon dioxide or water vapor, leaving the planet entirely barren. Prolonged stellar activity in the early stages of a star's existence exacerbates these issues. Unlike the Sun or similar stars, which stabilize relatively quickly, red dwarfs maintain high levels of radiation for much longer periods. This extended phase can lead to the complete loss of a planet's atmosphere, particularly if it's on a close orbit, as seen in the TRAPPIST-1 system. Research published this fall by Korsanson Totten and his colleagues shows that the fate of a planet's atmosphere depends significantly on its initial composition and proximity to the host star. If a planet has a dense hydrogen envelope, losing this primary atmosphere might still leave enough heavier elements to form a secondary atmosphere. So why might TRAPPIST-1e theoretically retain its atmosphere while TRAPPIST-1b remains barren? In their early stages of development, these planets likely form with substantial primary atmospheres rich in hydrogen and helium, captured during their accretion phases. However, the evolution of these atmospheres heavily depends on their distance from the host star and the star's activity during pre-main sequence stage. Modeling of TRAPPIST-1e indicates that the planet's initial thick atmosphere underwent significant changes as the planet's surface cooled and solidified from its molten state. At this stage, gases released from the magma ocean, such as carbon dioxide and water vapor, became dominant, while hydrogen escaped into space. The cooling period also allowed the formation of a secondary atmosphere composed of heavier molecules, less susceptible to erosion by stellar winds. In contrast, TRAPPIST-1b, which is much closer to its host star, was subjected to more intense ultraviolet and X-ray radiation. This intense radiation not only stripped away hydrogen, but also destroyed heavier molecules, leaving the planet with a thin atmosphere or none at all. Due to its proximity to the star, the planet remained too hot for the surface to cool quickly, prolonging the atmospheric escape phase. Research models such as Pac-Man-P provide detailed simulations of these processes. For TRAPPIST-1e, the interactions between its hydrogen-rich primary atmosphere and its silicate mantle played a crucial one. Hydrogen reacting with mantle oxides released water, which could accumulate in surface reservoirs. This process not only preserved a significant amount of volatile compounds, but also stabilized the planet's redox balance, which is critical for maintaining habitability. For TRAPPIST-1b, the same modeling results differ dramatically. A prolonged molten state and higher stellar flux led to the loss of even heavier molecules like carbon dioxide through hydrodynamic mechanisms. Consequently, the planet retained minimal volatile reserves, incapable of supporting a stable secondary atmosphere or surface water. Overall, these models highlight not only the divergent evolutionary paths of these planets, but also the importance of initial volatile composition and orbital position in determining a planet's fate. A secondary atmosphere, although thinner than the primary, can stabilize once the star transitions to a quieter phase. This stabilization depends on factors such as the planet's magnetic field strength, its ability to shield against radiation, and its capacity to retain heavier molecules that can sustain surface conditions favorable for life. In a recent interview, Dr. Joshua Christensen-Totten, co-author of the aforementioned study, provided a nuanced perspective on the challenges and potential for habitability in the TRAPPIST-1 system and similar red dwarf environments. At the center of the discussion is the dramatic pre-main sequence phase, a period lasting hundreds of millions of years during which red dwarfs emit significantly more radiation than during the main sequence phase. This elevated radiation leads to substantial atmospheric loss for nearby planets. Rapid cooling and the shifting habitable zone further complicate this evolutionary trajectory, with planets once scorched by high temperatures drying out, while more distant ones risk freezing as the star settles. Particularly striking is the idea of atmospheric recovery and retention over time. Dr. Christensen-Totten highlighted that planets within the habitable zone, such as TRAPPIST-1e, may condense water and other volatile substances into surface reservoirs as the star cools. This transition reduces the volume of the hydrogen-rich upper atmosphere, making it less vulnerable to stellar winds. His team's modeling suggests that, despite early challenges, such planets may retain secondary atmospheres through a combination of surface chemistry, cooling processes, and reduced radiation flux in later stellar phases. The interview also sheds light on the observational challenges. The interference posed by red dwarf variability complicates isolating planetary signals, especially for temperate zone planets. Despite these obstacles, continuous advancements in observational methods aim to overcome them. The prospects of future missions, such as the proposed Habitable Worlds Observatory, emphasize the need for reliable instruments capable of addressing these issues with greater precision. Dr. Christensen-Totten stressed the importance of differentiating atmospheric outcomes for planets under varying conditions. His research introduces a framework that considers the interplay between early atmospheric loss and subsequent stabilization processes. This system allows to highlight the resilience of some planets, suggesting that certain red dwarf systems may host stable environments capable of supporting life over their extraordinarily long lifespans, potentially spanning trillions of years. Each step in unraveling the mysteries of similar planetary systems brings us closer to understanding not only these distant worlds, but also the delicate balance that may allow life to thrive elsewhere in the universe. As our instruments grow increasingly sophisticated and our questions more precise, the answers awaiting us light years away could redefine our place in the cosmos. At some point of our lives, we have probably all wondered if we are alone in the universe. It would seem that in our own or in other distant galaxies, there are so many planets that revolve around numerous stars. So why have we still not encountered any traces of extraterrestrial life? But what if advanced alien life forms have been around for a long time, and they're simply hiding? According to the dark forest hypothesis, technologically advanced civilizations outside of the solar system may already be thriving. However, they have no intention of making contact because they are either cautious of potential attacks from other civilizations, or they may be indeed preparing to attack. Today, you'll learn about the dark forest theory and why you should probably be afraid of being heard by someone in the vast cosmos. 1. The dark forest hypothesis, the author and original source. The author of the Dark Forest Hypothesis, DFH, is science fiction writer Liu Cixin. It's worth noting that this is not a scientific theory, and it's not based on any concrete evidence. In 2008, Liu Cixin published his successful fiction novel titled The Dark Forest. The Dark Forest theory was first outlined in this book. The gist of the theory is that every civilization on a cosmic scale seeks to obtain the resources necessary for its continued survival. Therefore, any extraterrestrial life hides in order to not be destroyed by another civilization, and also in order to be able to attack and ensure its own survival. So why is this theory called the Dark Forest Hypothesis? In his novel, Liu Cixin compares this to precarious coexistence to a forest inhabited only by hunters. The author paints civilizations as metaphorical armed shooters in a dark forest, who silently move forward, afraid of being discovered by fellow hunters. If one hunter managed to find another, it's in their best interest to attack first before the enemy does the same. Based on this, we can name several ideas that are promoted by DFH. First one is that hypothetically, alien civilizations exist, but they are in hiding due to the risk of being attacked by others and losing acquired resources, such as inhabited planets. Within the construct of the dark forest hypothesis, survival as the basis of every civilization is known as the chain of suspicion. This phenomenon is caused by insufficient communication, which leads to mistrust as a direct result. The second idea is that a civilization that gives away its location by actively transmitting, say, radio signals, could be captured or destroyed by others for resources. The third concept is that fellowship in this type of system is exceedingly rare, since every civilization strives above all to survive through expansion. However, a treaty is possible if the terms are beneficial to both civilizations. Liu Cixin represents the universe as a battlefield for limited resources, where an alliance is practically impossible. Finally, it's important to note that in Liu Cixin's hypothesis, these hunters are analogous to civilizations with a high level of technological advancement. Therefore, if any civilization is not sufficiently developed to announce itself in space, it will either go unnoticed or it may become easy prey. 2. DFH is an answer to the Fermi paradox. As you may already know, in 1950, famous physicist Enrico Fermi, when discussing the phenomenon of flying saucers with his colleagues, unexpectedly asked, "Where is everyone?" referring to examples of extraterrestrial life which marked the beginning of the famous Fermi paradox. We discussed it in detail in this video on our channel. Fermi assumed that if our galaxy formed several million years before the birth of mankind, then it is possible that other civilizations could have emerged during this period, much older than Earthlings. Therefore, the Milky Way galaxy should be full of civilizations, which could pick up our signals due to their much more advanced technological development, as well as travel through the galaxy. However, so far we have not seen any traces of alien activity. Why haven't they visited Earth yet or come close to our planet? To determine the potential number of extraterrestrial civilizations that exist within our galaxy, the famous Drake equation was derived in 1961. However, we cannot use it to learn why alien creatures have not left any signs of their life. Therefore, at the moment, the Fermi paradox only has theoretical explanations. Additionally, according to physics professor Adam Frank, the probability that Earthlings are the only civilization in the universe is very small. 1 in 10 billion trillion, which is to say 1 times 10 to the 22nd. The professor suggests that our evolution was not unique and other civilizations could potentially have existed before us or even much longer before us. There are more than 70 hypothetical solutions to this issue, one of which is the dark forest hypothesis. Of course, we cannot check the veracity of DFH due to our current technological limitations. However, Liu Cixin's theory provides a logical explanation as to why we still haven't picked up a single alien signal or found any clear signs of life on other planets. It's simply dangerous for other civilizations to betray their location for fear of invasion. Although this hypothesis presents very clearly defined ideas, DFH still has some inaccuracies. For example, if other civilizations exist, then they must differ from ours when it comes to the level of development due to different periods of origin, as Fermi pointed out. This means that there may be civilizations of our technological level or higher that actively search for alien life or study their own systems just like us, because they don't see it as a threat. Therefore, we may not be the only ones sending signals out there, because civilizations do not necessarily develop in fear of detection if they have not experienced confrontation. 3. More about the assumptions of dark forest hypothesis. The idea of capturing other territories and the possible destruction of the first civilization on a cosmic scale is reminiscent of our historical experience on Earth, namely colonization and wars. There are a lot of reasons why people conquer and establish power over other nations. However, in most cases, such as during the colonization of Africa by the Europeans in the 19th century, the main motivation were land and natural resources. The rapid industrial development in Europe required more resources, which were abundant on another continent. Therefore, the colonization of Africa contributed to the development of European countries, but the African land and its population suffered from this expansion. The DFH offers the same colonial model as the reason why one civilization would attack another. We're still pursuing the goal of expansion for the continued survival of mankind, studying exoplanets and other star systems, and planning the colonization of Mars. The red planet is also rich in natural resources that are needed for technological development. Therefore, if we assume that another civilization pursues the same goals, we may have to fight for lands that could serve humanity. Otherwise, our survival would be under threat because, according to this hypothesis, survival and the necessary resources are crucial for the preservation of the species. In addition to the need to replenish a limited resource, there are other reasons for the aggressive behavior by civilizations. For example, as we've already said, the DFH introduces a concept known as the chain of suspicion. This concept is closely related to another aspect of this hypothesis, which is known as the technological explosion. The gist of the chain of suspicion is that it's impossible for civilizations to know whether others are benevolent or hostile. These doubts can lead to preemptive attacks and self-defense. According to the researcher Chao Yu, this chain can only emerge between civilizations with the same level of technological development, since they can likely objectively assess their own and other people's capabilities. Thus, if there is a significant gap in their respective levels of development, the chain cannot be formed. The technological explosion describes the ability of cosmic civilizations to make rapid scientific and technological leaps. A strong new hunter can pose a threat to others, because advanced civilizations can start to be wary of it or seek to destroy it. However, Chao Yu points out that any invasion attempt could also harm the attacker, as other civilizations with similar or higher levels of advancement would be able to detect it, which would contribute to the chain of suspicion. However, in spite of the clear advantage in attacking other civilizations and in stealth, the DFH considers another scenario: benevolence. The point of benevolence is to refuse to attack other civilizations, even if they are detected, and they will probably be able to respond to the signal. In a dark forest, this tactic is very dangerous because it is again reinforced by the chain of suspicion. Found by a benevolent civilization, another civilization may turn out to be aggressive or rapidly developing. Therefore, in the future, it will be able to destroy others and survive, having collected enough resources, whereas the benevolent civilization will most likely cease to exist. If we assume that extraterrestrial life really exists, and it is way more advanced than us, then it might attack us, since this is a survival tactic with the highest chance of success. This is not the best news. So then, are there other ways for the events to unfold that are beneficial for Earth based on the dark forest hypothesis besides an attack on our planet? Let's look at this in terms of game theory. Number 4, game theory and DFH. The point of game theory is to learn how people make decisions based on certain conditions in order to achieve the best result. So let's imagine Earth as civilization A and a more advanced alien life as civilization B. Let's assume that B has picked up on our radio signal. Now B has 3 strategies for action: attack, remain unnoticed but become suspicious, or respond with a prospect of possible friendship. Attack will be considered the most advantageous strategy, even if A is able to fight back. On the other hand, this scenario might turn out to be a losing one for B if A, according to researcher Alina Su, can send a signal in order to transmit the coordinates of the planet of civilization B to other civilizations. Perhaps in this case, the best option would be to remain unnoticed. If both civilizations don't do anything, neither will benefit. On the one hand, this will save A and B from danger, but on the other hand, they won't be able to obtain the necessary resources. There's also an option to make friends. If both civilizations agree to an alliance, then one of them will benefit, for example, from the ability to use alien technology. The other civilization, the one that proposed friendship, would also be able to benefit, albeit slightly less. Does that mean that an alliance is the best scenario for both civilizations? Possibly, but it comes with some caveats. Firstly, benevolence, as you already know, is very dangerous because, hypothetically, extraterrestrial civilizations are unlikely to be friendly too often. Secondly, the potential amount of resources that would be obtained, even if a trade deal is established, is less than what you would gain with a forced takeover. And so, the theoretical attack on Earth has the highest probability, but this course of events can greatly harm the attacker. Still, other civilizations may be afraid of the unknown military potential of Earth, and therefore choose the tactics of secrecy or friendship. 5. The danger of sending signals into space. Does it mean that if the probability of Earth being conquered is higher than any other option, should we be wary of the propagation of our signal into space? According to DFH, messages to other civilizations could threaten our security. The same opinion is shared by many astrophysicists, including Stephen Hawking. After a breakthrough in space research in the middle of the last century, there was plenty of interest from scientists in the search for alien civilizations. In 1974, the famous Arecibo message was sent to a star cluster 21,000 light-years away. Since that time, several radio messages have been launched into space, the latest of which dates back to 2017. Physicist Stephen Hawking believed that these messages could lead to the scenario described in The Dark Forest. According to him, an alien civilization visiting Earth could have the same consequences for us as the effects colonization of America had on its native inhabitants in the 15th century. Therefore, he expressed an opinion that this type of communication must be stopped. Nonetheless, other scientists, including SETI astrobiologist Douglas Vakoch, believe that the fear of sending messages can lead to Earth's isolationism. Moreover, Vakoch pointed out that the alien civilizations have had a chance to attack our planet while it was just developing, so you should not be afraid of the possibility of being heard by extraterrestrial life. Finally, the dark forest hypothesis also promotes the idea of differences in hunters' behavior. That is, not all alien civilizations would definitely attack us if they detected our signal. Additionally, a group of independent researchers led by the Global Catastrophic Risk Institute, Seth Baum, suggested that in addition to potentially dangerous civilizations, those with a lesser potential to harm us may also exist. They believe that there might be neutral civilizations that prefer to hide and not make contact, as well as civilizations that could establish a friendly relationship with Earth and help us solve global problems. In conclusion, the dark forest hypothesis is not the sole answer to the burning question, where is everyone? There are many other suggestions that attempt to explain the lack of a hint of extraterrestrial life, such as too great of a distance between civilizations, or the low likelihood of the emergence of other living organisms. Nevertheless, we cannot rule out the possibility of the veracity of Liu Cixin's theory, but we cannot confirm it either. Our planet appears as a serene oasis against a vast cosmic desert. But beneath this calm facade lies a dynamic force, invisible but powerful, constantly shaping our world in invisible ways. For millennia, mankind has looked to the stars to find their way, unaware that an invisible guide silently guided them. This guide, the Earth's magnetic field, an invisible shield, was our silent protector, shielding us from the merciless solar winds and cosmic radiations. But what if this constant of our lives was on the verge of a colossal change? A change is so profound that it could change the way we live our lives. Deep beneath our feet, in the heart of our planet, lies the key to this mystery. A restless ocean of molten iron is churning, creating a magnetic force that envelops our world. But this force is not as constant as we once thought. Scientists have unearthed evidence hidden in the very bowels of our planet that tells the story of an ever-changing world, of flipping poles, changing the direction of the magnetic field, and turning the world as we know it upside down. This is the story of Earth's geomagnetic inversions, a phenomenon as mysterious as it is fascinating. Our story begins with an invisible force that has imperceptibly changed the course of our planet's history. That force is the Earth's magnetic field, a complex and dynamic energy that extends far beyond the planet's surface into the space around us. Since ancient times, this magnetic field has been a silent guide for explorers and mariners, leading them through uncharted waters. It is a force so subtle that it goes unnoticed, yet so powerful that it has played an important part in the survival and development of civilizations. Deep inside the Earth is the heart of this magnetic force. Here, in the outer core, a bubbling ocean of molten iron generates the magnetic field. This motion, caused by the Earth's rotation, creates the dynamo effect, a process that maintains the magnetic field for billions of years. This field is not just a landmark for navigation. It is a shield. It reflects harmful solar winds and cosmic radiation, protecting our atmosphere and ensuring the survival of life on Earth. But this guardian is not as unchanging as it seems. Throughout Earth's history, the magnetic field has undergone dramatic transformations, geomagnetic inversions. These are periods when the magnetic poles change, north becoming south and vice versa. Evidence of these changes is captured in the very stones of our planet. As volcanic lava cools and hardens, the minerals within it align within the Earth's magnetic field at the time. By studying such rocks, scientists have discovered that our planet has undergone many changes. These changes do not happen suddenly. They occur over millennia. The field weakens, becomes chaotic, and gradually restores the opposite orientation. The reason for these changes remain one of the greatest mysteries of geoscience. As we delve deeper into this mystery, we begin to realize the immense power and fragility of this invisible shield. The history of the Earth's magnetic field is a story of constant change, a reminder of the dynamic nature of our planet. As we delve into the past to unlock the mysteries of geomagnetic inversions, we turn to the Earth itself, our most reliable historian. The geologic record contains evidence of these monumental shifts. Volcanic rocks, especially basalt, have become invaluable in this kind of research. As we mentioned, as the lava cools and hardens, the tiny magnetic minerals within it align with the Earth's magnetic field. This natural recording process created a timeline of the Earth's magnetic history locked within these ancient rocks. While studying these rocks, geologists discovered a startling fact. Over the last billion years, the Earth's magnetic field has reversed hundreds of times. The most recent of these reversals, the Bruns-Matayama reversal, occurred about 781,000 years ago. These reversals are irregular and unpredictable, with intervals ranging from tens of thousands to millions of years. This process is gradual and takes thousands of years. Another piece of evidence comes from the ocean floor. Here, magnetic striping, bands of rock with alternating magnetic orientation, coincide with mid-ocean ridges. As new rocks form and spread out from these ridges, they record the current orientation of the magnetic field, creating a symmetrical pattern of these reversals on either side of the ridge. Scientists have recently observed changes that hint at a potential upcoming reversal. Satellites and observatories have detected a gradual weakening of the magnetic field and increased movement of the north magnetic pole. The magnetic North Pole, once firmly established in the Canadian Arctic, is now drifting with acceleration toward Siberia. This movement, although not a definitive sign of an imminent reversal, is a clear indication of the dynamic nature of the magnetic field. Other indications include the development of the South Atlantic anomaly, an area where Earth's magnetic field is much weaker. This anomaly grew and deepened over time, affecting satellites and spacecraft. As we piece together these clues from the past and present, the history of geomagnetic inversions becomes clearer. These historical and contemporary observations not only reveal the dynamic nature of our planet's magnetic field, but also remind us of the ever-changing nature of the world in which we live. To understand the mechanics of geomagnetic inversions, we must travel deep into the heart of the planet, to a place where intense heat and pressure produce one of the most mysterious phenomena on Earth. A core located at the center of the Earth is divided into two parts, a solid inner core and a liquid outer core. The outer core, consisting mainly of iron and nickel, is in constant motion due to Earth's rotation and thermal convection. The movement of liquid metal generates electric currents, which in turn create magnetic fields. This process, known as geodynamo, is the driving force behind Earth's magnetic field. The dynamics of the outer core are complex and not fully understood. However, scientists believe that the Coriolis effect, a consequence of the Earth's rotation, plays a decisive role in the configuration of the magnetic field. The Coriolis effect causes convection currents in the outer core to spiral, creating swirling vortices. These vortices are thought to organize magnetic field lines, keeping the magnetic poles aligned. But what happens during a geomagnetic reversal? Current scientific understanding suggests that these reversals begin with a weakening of the magnetic field. This weakening can disrupt the alignment of the force lines, making them unstable and chaotic. As the field is weakened, the influence of the Coriolis effect on the motion of the outer core decreases. This reduction in influence allows the magnetic field lines to realign in the opposite orientation, effectively reversing the poles. But let's consider the Earth's magnetic field not only as a compass reference point, but also a vital protector. The invisible shield, built deep inside the planet, is our first line of defense against harsh solar radiation and cosmic threats. The Sun, a fiery cauldron of nuclear reactions, constantly emits solar winds, streams of charged particles that can be devastating to life and technology. However, the Earth's field deflects these particles, creating a safe harbor for life to flourish. This magnetic shield also protects us from cosmic rays, high-energy particles, distant supernovae, and other cosmic events. Without such protection, these rays could pose a serious threat to humanity's biological systems and electronic infrastructure. However, during a geomagnetic field inversion, this protective shield is significantly weakened. This weakening can lead to an increase in the radiation impact on the Earth's surface. The potential consequences of such increased radiation are profound. It can affect climatic conditions, potentially lead to dramatic changes in weather. Elevated radiation can also have biological consequences, affecting everything from human health to the behavior of animals, especially those that use magnetic fields to navigate. Moreover, a weakened magnetic field could leave our technology vulnerable. Satellites, power grids, and communication systems could be jeopardized by increased solar and cosmic radiation. These simulations show that the magnetic field is in turmoil, with multiple poles appearing and disappearing and magnetic lines of force moving and changing in a complex pattern. This study of the Earth's magnetic field as a dynamic protector not only highlights its importance, but also emphasizes the need to understand and prepare for potential problems resulting from its weakening during a geomagnetic reversal. What about the potential global implications of a geomagnetic reversal and humanity's preparedness for such an event? This phenomenon, although a natural part of the Earth's geological cycle, poses serious challenges in our technologically oriented world. On the one hand, geologists discuss the likelihood of such an event, emphasizing its inevitability given Earth's history. However, scientists express concern about the vulnerability of our satellite networks, power grids, and communication systems. A weakened magnetic field could lead to increased solar radiation, potentially disrupting such critical technologies. Also, let's not forget about possible climate change. Although the exact effects are unknown, some models suggest that shifts in the magnetic field could affect weather patterns, potentially leading to extreme and unpredictable weather patterns. One thing is certain: the impact on wildlife, especially migratory species like birds and marine animals that use magnetic fields for navigation, and that could be catastrophic. Disturbances can lead to ecological imbalances and affect biodiversity. Research aimed at understanding and predicting the timing and consequences for geomagnetic reversals is ongoing. The need for global cooperation in such research is key to developing strategies to mitigate potential risk. It is a reminder that while we may not be able to prevent natural events of this magnitude, through understanding and preparation, we can mitigate their impacts. As we near the end of our journey, we turn our attention to the future, specifically how scientists are tracking and predicting changes in the Earth's magnetic field. At the forefront of this research is a fleet of sophisticated satellites equipped with instruments capable of measuring all the subtleties of the magnetic field with unprecedented precision. Projects such as the European Space Agency's SWARM mission provide valuable data on magnetic field strength, direction, and anomalies. These satellites are complemented by a network of ground-based observatories that continuously monitor the magnetic field at various points on the Earth's surface. Together, these instruments offer a comprehensive view of the behavior of the magnetic field and its variations over time. The data collected are not just for scientific curiosity. They play a crucial role in predicting the future of the Earth's magnetic field. By understanding the patterns and causes of past geomagnetic reversals, in the vast expanse of space among countless stars and galaxies, there is a whisper. The whisper of a distant star that's traveled light years to reach us here on Earth. This is not a science fiction tale, but a reality of our universe, a testament to the continual growth of our understanding of the cosmos. Scientists eavesdropping on space have detected a signal, a radio wave, from a star system not so different from our own. A star known as YZ Ceti is located just 12 light years away. But it's not just any signal. This signal carries a potential signature of a magnetic field very similar to the one that protects our own planet. The magnetic field that may envelop a rocky Earth-sized exoplanet orbiting YZ Ceti. What could it mean? Could this distant world be more like our own than we've ever imagined? And what could it tell us about the search for life beyond our solar system? Let's go light years across to delve into the mysteries of radio signals in space and explore the magnetic fields of distant worlds. In the boundless silence of space, radio signals can, without guile, be called whispers. But what are these signals and how do they propagate over such vast distances in space? Radio signals are a type of electromagnetic radiation, just like light, X-rays, or microwaves. They're generated by a variety of sources, from stars and galaxies to artificial satellites and spacecraft. These signals travel at the speed of light, carrying information across vast distances in space. They can tell us about the composition of stars, the presence of planets, and even the origin of the universe itself. But how do we detect these signals? The answer lies in the technology of radio astronomy. Radio telescopes, such as the Very Large Array in New Mexico, or the now-defunct Arecibo University in Puerto Rico, are designed to detect and analyze radio signals from space. They are our ears to the cosmos, listening to the faint whispers of the universe. Once a signal is detected by a radio observatory, it is analyzed using sophisticated algorithms and computer models. These analyses can provide extensive information about the source of the signal from its location and distance to its physical properties. But radio signals from space are not just a scientific curiosity. They also have practical applications. For example, radio signals from satellites are used for GPS navigation, weather forecasting, and Earth observation. They are an integral part of our modern technological infrastructure. So, the next time you look up at the night sky, remember, there's a whole symphony of signals playing out there, a cosmic conversation, an orchestra that we're just beginning to understand. Let us return to the constellation of Cetus, the sea monster, in which lies a star that whispers to us across light years. Her name is YZ Ceti. YZ Ceti is a red dwarf, smaller and cooler than our Sun. It is located 12 light years away, a close neighbor on a cosmic scale. But what makes YZ Ceti truly fascinating is not the star itself, but what revolves around it. At least 3 exoplanets are known to orbit around YZ Ceti, the innermost of which, YZ Ceti b, is of particular interest. YZ Ceti b is a rocky, Earth-sized exoplanet that orbits very close to its parent star. In fact, it is so close that its year, the time it takes to make one revolution around YZ Ceti, is only 1.6 Earth days. Recently, using Very Large Array, scientist at Bucknell University, Professor Jackie Villadsen, and her colleague J. Sebastian Pineda detected a repeating radio signal coming from YZ Ceti. The signal was recorded at a frequency of 2 to 4 gigahertz. It appears to be modulated by the rotation of the star and the orbit of YZ Ceti b, indicating an interaction between the star and the magnetic field of the planet. This discovery could have major implications for our understanding of exoplanets and their magnetic fields. Although YZ Ceti b is unlikely to be teeming with life due to its close proximity to its star, the detection of its magnetic field is important because it provides a method for discovering more life-friendly worlds in the future. But what does this signal really mean? And why are magnetic fields so important in our search for life? To answer these questions, we need to look deeper into the invisible force fields that shape our universe. Magnetic fields are a fundamental force of nature. They guide the hand of the compass, help birds navigate their long migration, and protect our planet from the harsh solar wind. But magnetic fields are not just an earthly phenomenon. They also play an important role beyond the Earth. Our Sun, for example, has a complex and dynamic magnetic field. It controls the Sun's activity from the formation of sunspots to the eruption of solar flares. Magnetic fields also shape the structure of galaxies, directing the movement of interstellar gas and influencing the formation of new stars. But perhaps the most intriguing role of magnetic fields in space is their potential impact on planetary habitability. A strong magnetic field can protect a planet from harmful radiation from its star, helping to maintain a stable atmosphere, and perhaps even conditions suitable for life. That's why it's so interesting to detect a potential magnetic field on exoplanet YZ Ceti b. This could provide valuable information about the planet's atmosphere and its potential to support life. How do magnetic fields affect the detection and interpretation of signals from space? To understand this, we need to delve a little deeper into the nature of radio signals and magnetic fields. Radio signals are a type of electromagnetic wave, which means they are composed of oscillating electric and magnetic fields. These fields can interact with other magnetic fields they encounter as they travel through space. When a radio signal passes through a magnetic field, it can be altered in various ways. Its direction can be changed, a phenomenon known as deflection. Its polarization, or the orientation of its electric field, can be rotated. Its frequency, in other words, the number of waves passing through a point in a given time, can be shifted. These changes can provide valuable information about the magnetic field that caused them. By studying these changes, scientists can infer properties of the magnetic field such as its strength and orientation. But magnetic fields can also pose problems for detecting signals from space. They can cause interference, making it difficult to detect the signal. They can distort the signal, making it difficult to interpret. This is why the study of magnetic fields is so important in the field of radio astronomy. By understanding how magnetic fields affect radio signals, scientists can develop methods to correct these effects and extract valuable information hidden in signals from space. To better understand the influence of magnetic fields in creating favorable conditions for life on the planet, let's turn our gaze closer to home, to a familiar red-headed neighbor in our cosmic backyard. Mars, the red planet, has long captured our imagination. With its towering volcanoes, deep canyons, and hints of liquid water, it is one of the most intriguing places in our solar system. But Mars also presents us with a mystery. Unlike Earth, Mars has a very weak and inhomogeneous magnetic field. This has serious implications for the planet's atmosphere and its ability to support life. Mars' magnetic field is not created by a dynamo in its core like Earth's. Instead, it's the remnants of magnetism trapped in the planet's crust from the time when Mars actually had a global magnetic field. Without a strong magnetic field protecting it, Mars's atmosphere is directly exposed to the solar wind, a stream of charged particles emitted by the sun. Moreover, new models presented by R. Sakata of the University of Tokyo and others suggest that a weak magnetic field like Mars after its dynamo is turned off could actually lead to a more rapid loss of atmosphere than if there were no magnetic field at all. Modeling has shown that a weak magnetic field results in the fastest rate of atmospheric ion loss, 6 times faster than without a magnetic field. The reason is that the weak magnetic field strength lines were easily repelled by the solar wind, creating a path for ions to escape into space over the night side of Mars. This suggests that Mars' remaining magnetic field may have hastened the planet's transformation into the cold and barren world it is today. Over billions of years, this caused Mars to lose much of its atmosphere, a process known as atmospheric stripping. This turned Mars from a potentially warm and wet world in its early history into the cold and dry planet we see today. The case of Mars provides a vivid illustration of the importance of magnetic fields to a planet's habitability. It shows us that without a strong magnetic field, a planet, even one as Earth-like as Mars, can lose the things that make it habitable: atmosphere and water. By the way, we've already looked at the problems and potential solutions to make Mars a second home for humanity in a separate video. Exoplanets, planets orbiting stars outside our solar system, have recently become a major focus of astronomical research. With more than 1,000 discovered to date, they offer a wealth of opportunities to learn about the diversity of the planetary systems in our galaxy. One of the most exciting developments in this field was the discovery of the first known magnetic field on an exoplanet in late December 2021 by an international team of astronomers who used the Hubble Space Telescope for their research. It was discovered on a Neptune-sized planet called HAT-P-11b. HAT-P-11b is located about 123 light-years away in the constellation of Swan. It is a hot Neptune, a type of exoplanet that's similar in size to Neptune, but much closer to its star, resulting in high temperatures on the planet's surface. The detection of a magnetic field on HAT P11b was a groundbreaking discovery. It showed that exoplanets can generate magnetic fields just like planets in our solar system. As we mentioned earlier, studying the magnetic fields of exoplanets can provide valuable information about their internal structure, atmospheric properties, and potential habitability. For example, a strong magnetic field can protect a planet's atmosphere from stellar winds, helping to preserve conditions that could support life. That brings us back to YZ b, an exoplanet from which a signal was recently detected. If this signal is indeed indicative of a magnetic field, it could have a major implication for our understanding of this exoplanet and its potential for life. Traveling through space from the familiar landscapes of Mars to the far reaches of YZ, we've truly come to realize the invisible power of magnetic fields, their profound effect on planets, and their potential to harbor life on them. The field of studying signals from other galaxies has grown rapidly over the past few years. For example, the Giant Metro-Wave Telescope in India has detected a faint signal from the most distant galaxy to date. The signal detected by YZ Ceti opened another new window into the universe, reminding us how much we still have to learn about our world. As we look to the future, the study of signals from other galaxies will continue to be the focus of space research. Each signal carries the potential for new discoveries. So when we look up at the night sky, let's remember that we're not just looking at stars and galaxies. We're looking at a universe filled with unseen forces, whispered signals, and hidden possibilities. And as we continue to listen and explore, who knows what we might discover next? Are we alone in the universe? Those involved in the search for extraterrestrial life have been increasingly sharing the view that mankind is not ready for contact with the alien civilization. It becomes obvious the moment we put the dreams and imagination aside and delve into the scientific approach. Not only can the search for intelligent civilizations be fruitless, but it can also lead to opening the door that we are not ready to walk through. What mysteries actually hide behind the cosmic silence? And why do we put so much effort into coming in contact with extraterrestrial beings, knowing that we may never achieve this goal? After spending years exploring the possibilities of coming into contact with extraterrestrial beings, scientists had come to surprising conclusions. Let's imagine that alien civilization is at the same level of technological advancement as us, and their spacecrafts fly at the same speeds as ours. Turns out intelligent life with this advancement level needs less than 1 billion years to spread across a galaxy of the same size as ours. Just look at how fast the galaxy would actually have been inhabited by any civilization of this caliber. But if that were the case, why are we not seeing this lively galaxy around us? To answer this question, we'll need to take a look at the Kardashev scale. The majority of modern scientists use this scale to measure the potential ability of living organisms to colonize the surrounding space and subsequently the possibility of contact with other life forms. This scale gives its own answer as to why we are not seeing this image of populated space all around us. Kardashev proposed to measure a civilization's level of technological advancement based on how efficiently it uses their energy resources. According to this scale, a Type 1 civilization can learn to utilize all of the energy that they're able to harvest on their home planet, radiating from its parent star. This type of civilization is most likely ready for interplanetary travel and at some point down the line will be able to colonize its entire system. For context, we only use 73% of the planet's energy potential, whereas the amount of energy we learn to harness from the sun is less than 0.1%. Turns out we're still on level 0, according to this scale. Civilizations that have reached the status of Type 2 are capable of capturing the energy not only on their home planet, but also any energy they could harness within their star system. Or at the very least, they're close to being able to do that. In their search for this type of civilization, scientists are on the lookout for a Dyson sphere, a hypothetical artificial structure that would allow the civilization to harness all of the star's energy from within the system. These civilizations would be capable of interstellar travel. They will have actively colonized their own galaxy and possibly moved on to colonizing the surrounding areas, which would allow them to keep increasing the amount of energy that they could use. As well as using all of the energy of their star system, Type 3 civilizations are able to harness the energy from neighboring systems, control the energy of their entire galaxy, or even the entire universe. These civilizations are able to not only control this energy, but possibly change entire worlds. There's a simple reason as to why communicating with the Type 1 civilization is problematic. Upon calculating the capacity at which we can transmit and receive signals in space, we come to find that the maximum visibility of the Earth's energy activity, radio signals, lasers, electric activity, is very limited. We can only be seen or heard from a distance of 4 light years. The noise we create could only be heard by our closest neighbors who have reached the same level of development. Type 2 civilization would be able to hear us from much further away. They would also be able to ensure they remain unnoticed, either because of the great distance or because they wish to keep it that way. After 60 years of transmitting various signals and scanning the skies trying to detect artificial signals, we haven't been able to find anything and we remain unheard. The paradox of great silence was first raised by legendary physicist Enrico Fermi. Speaking to his colleagues once, he raised a seemingly simple question. Where are the aliens, and why have they not been to visit us? However, when you consider our civilization's level of development, the answer is pretty obvious. Why would they? The logistics required for interstellar travel are only available to civilizations that have reached Type 2 at least, and in their eyes, we're not worth it. What person in their right mind would try to communicate with ants? How would an ant be able to recognize that someone's trying to communicate with it? After all, in terms of our development and technological advancement, compared to them, we're akin to highly developed ants that have taken over an entire planet, not to mention the ineffective use of said planet's potential. Other civilizations that, like us, haven't yet reached Type 1, they stay confined to their own planet and star system. It's simply unrealistic to expect any guest from a place like that. It is possible that right at this moment they're working on the same problems as we are: starvation, fighting for resources, and pursuing minor and major wars for territories. And so it appears that Type 1 civilizations would simply have other things to worry about. However, is it possible that someone could have overcome those issues and decided to launch themselves into space? The data presented by the scientists suggests we may in fact have a surprisingly large number of neighbors. As we lift our gaze to the cloudless sky, we can imagine how many potential inhabited planets there are. What we see in the sky is only 1% of our own galaxy, the Milky Way. Even if only 1% of these worlds are inhabited and populated with conscious life, that would amount to around 100,000 intelligent civilizations that could exist in our galaxy alone. And they all remain silent. There are a vast number of solutions to the Fermi's paradox, because there are around 100 scientific theories alone that attempt to explain this silence. Let's break down the most interesting of those theories. There are no signs of Type 2 or Type 3 civilizations because they don't exist. The scientific analysis tells us there are thousands of civilizations in our galaxy alone, hence they presume that there is a factor that stands in the way of their development. This factor is called the Great Filter. This theory suggests that after reaching a certain level of development, life faces an obstacle that's impossible to overcome. However, scientists don't know what this great filter may be. The possibilities are only limited by our imagination, from artificial intelligence which cleanses the overly developed organic life from the galaxy, to various forms of apocalypse. The most unfortunate thing about this theory is that, if true, humanity is faced with three possible prospects in the future. According to the first scenario, we as humanity are a unique life form that has managed to overcome the big hurdle of the Great Filter. That would mean that reaching our level of progress is very challenging, and the chances of it happening are very low. In this case, the cosmic silence would be caused by the majority of civilizations failing to overcome the Great Filter. Hence, we simply have nobody to come in contact with. The second scenario suggests that we happen to be the first ones among our neighbors to advance to this level. This would be due to the fact that the conditions necessary for the existence of conscious life had only been established relatively recently, and we happen to be the pioneers of this progress. In this case, we simply found ourselves in the right place at the right time to have become one of the first ultra-intelligent civilizations. It also means we have plenty of time to advance to become a Type 2 and Type 3 civilization. That's the reason why there's no hope for contact. We are progressing faster than any other organic form of life since the Big Bang. The third scenario presented by scientists is more pessimistic. They reckon that if we were not the first ones to reach this level of advancement in this rare sequence of cosmic events, then the Great Filter is still ahead of us. They think that life evolves at regular intervals until it reaches a certain stage, which is where we stand now. Whatever or whoever it is, it presents a challenge that prevents life from evolving to a Type 1 civilization, and it's unlikely that we would be an exception to this rule. Those favoring the third hypothesis believe that the cosmic silence is great news for us. After all, the presence of complex life on Mars, Moon, or somewhere else means that the Great Filter is bound to be ahead of us. There's also an opposing viewpoint. According to it, Type 2 and Type 3 civilizations do exist, and we haven't come across them for a reason. This is based mainly upon the fact that we're very much limited in our search. After all, we are searching for the signals that are only 100 light years away from us, which represents a mere 0.1% of our galaxy. The most interesting theories resulting from this version sound like this. Galaxy has long been colonized, and to the colonizers themselves, we are located in a low-interest deserted area. The perfect example of a similar situation happened in Earth's history: colonization of North America. Native Americans residing in the remote parts of the continent only learned about the presence of their neighbors, super-developed Europeans, several decades after the latter arrived on the continent. It's also possible the activity is present around our system. We're simply too primitive to understand these signals, or we are focusing our efforts elsewhere. That would be like trying to communicate with people using the internet via Morse code. It is equally possible that our minds differ so greatly compared to other life forms that our attempts to establish contact come across as senseless noise. Another interesting hypothesis is the cosmic zoo theory, which states that we are actually surrounded by a densely populated galaxy. Within this world, Earth is something akin to a wildlife reserve, the kind you could watch, but you're not allowed to go on a safari ride or make contact with such a primitive life form. And still, every attempt to explain this paradox inevitably comes to a stop. We still know very little about space, and we have not yet evolved to the level necessary for resolving these problems. But that doesn't mean that our attempts to find intelligent life have stopped, and humanity is frozen in place, waiting for outside contact. There are currently at least 2 projects that have spent several decades trying to establish contact and search for extraterrestrial life. These are the projects SETI and METI. The work of these 2 projects is based on the Drake equation, a mathematical formula that suggests it's possible to accurately calculate the number and, more importantly, the potential location of inhabited worlds. The next step is to use this information to reach out. According to this equation, our galaxy hosts between 8 and 2,900 systems of intelligent life. As science evolved and our knowledge about our galaxy grew, the calculations became more precise. Realistically, there should be 36 other brother worlds coexisting with us in the Milky Way galaxy. The SETI project started in 1984, and at first it focused on scanning our immediate surroundings in search of artificial radio signals coming from our potential neighbors. However, no signals were found. Right now, the major hope is that the European Space Telescope Gaia will bring some results. It's able to transmit information about the exact location of all stars in our galaxy and give an accurate assessment of every star system's potential. That's why the SETI project was able to move on from a rough estimation of various star systems to a detailed analysis of each one, thanks to a technological advancement. And now, every signal sent out there is directed towards the systems with the highest likelihood of intelligent life. Will we get a response from any of them? The answer to this is both yes and no. Some of the systems we have already researched are so far away that any response from them would take over 3,600 years to reach Earth. And last but not least, the mission of METI is also very important. After all, they help by trying to capture any messages from space and send our greetings to distant stars. We know of at least 8 attempted communications, 2 of which are the famous gold records on the Voyager probes and similar ones on the Pioneers. The other 6 are messages contained in radio signals directed towards some stars. For example, to one of the nearest solar-type stars, Gliese 581. So far, there have been about 40 radio sessions in total. We're unlikely to hear a response to them, but it is possible that our descendants might. To sum up the results of our small study, we can say quite definitely that the silence of the universe is normal. It's also possible that we have not yet sufficiently evolved to make contact with the intelligence around us, or even that the cosmos itself is not yet ready for this. Which one of these scenarios is the most likely? Are we a unique species, or has the entire space been colonized by super-developed civilizations for a long while? We are close to uncovering the answers to these questions. But are we ready for this contact?